What we're going to do now is try and implement the Blin-Fang model with WebGL. So in this first part, what I want to do is look at what kind of functions are in MVJS to help you with that. What we'll see is that there's a few in there, sort of utility-like functions, but basically the shader itself, how you combine the various terms, how you do diffuse, specular, and ambient, you're going to have to either build those models yourself, or actually the sample code has them done for you. And in subsequent lecture or two, we'll actually look at the shaders, because there's going to be some choices you have to make about where to carry it out in the vertex shader, in the fragment shader, or even as today we'll see it, you can actually carry it out in the application, because all we're going to be looking at today is flat surfaces like polygons, and I'll show you the shaded cube later in this lecture. Okay, so what do we need to do that? Well, we've seen this all before. You need normals at every point you want to compute a color. You need the material properties, and you need the various lights. We're going to just do one light for today, but every light you can define the same way. Well, there used to be functions for every one of that. There was a function in the old fixed function pipeline called GL normal, and you gave it the x, y, and z directions of the normal vector, and that was used put as part of the state. So there was a present normal, like other state variables that stay the same until change. So if you're dealing, say, with a flat polygon, that normal defined once would be used at all of the other vertices. Likewise with materials, you could define all of the material properties we've talked about for the red, green, and blue components, for ambient, specular, and diffuse components. Likewise for point sources, and there were a few things you could do with these deprecated functions. There were others that would let you define spotlights. You could define the direction of a spotlight and how much of an angle the spotlight went over. But those turn out to be pretty easy, as you'll see, to implement ourselves. And rather than carry them out within the application, which is what the old OpenGLs would do, is do the lighting calculation there. Now, by doing these functions ourselves, we can carry out those lighting calculations wherever we think best. Now, we also said when we derived the models that we wanted things to be normalized, and so we'll use a normalization function both within GLSL, and also there's one, as you'll see, within MVJS. We've said that if you normalize early for most applications, the further calculations will be simplified because things are already be normalized. We're always using the fact that we want to use cosines rather than angles, because they can be computed using the dot product, and if the vectors are pre-normalized, then the dot product is in fact the cosine of the angle. We also, as we go through this, you'll see places that you have to be a little careful of what happens when you apply various transformations, because one of the things you have to decide when you're doing lighting and shading and other techniques we'll be coming to is what space do you really want to carry them out in? Do you want to carry them out in object space? Do you want to carry them out in the camera space? Or do you want to carry them out in some other spaces that we'll introduce? And so one of the things you'll be doing, as you'll see, is we'll be transforming various vectors into different spaces. And one of the things we have to be careful of is what happens to things that we've normalized, because if the length of the vector changes, then we have to do a normalization again, and that of course has an impact on efficiency. But more the problem is that if you don't do the normalization, your lighting calculations can come out terribly wrong. So one of the things to keep in mind is that rotation and translation don't change lengths, but scaling does. And so if you keep track of where you might have done scaling, then you could see where renormalization might be needed. Okay, so let's look at a simple case, and this is basically all we're going to need today is to look at the normal for a triangle, and this is what we had in the last lecture. If you know the 3 points for the triangle, P0, P1, P2, which is kind of the normal situation in WebGL, you define the triangle and other entities by vertices, so that's the form we usually have our data. Then you can just take P1 minus P0 to get one vector in the plane and P2 minus P0 to get another and take their cross product. Now, we're not worrying about degenerate cases because things start falling apart when P1 and P2 are the same. We're assuming we have 3 distinct non-collinear points. And then we could easily normalize that and say our normal is that we're going to use is the normalization of this of a normal vector. Right-hand rule, be careful of that because generally you want the normal to face outward from the face, so you'd want to go P1 minus P0 and P2 minus P0. If you swap one of them, then you wind up changing the direction of the normal. Okay, now what about light sources? How do you specify them? Well, we're going to specify them by just using Vec3s or Vec4 types. What do you have to specify? You have to specify the red-green components, red-green-blue components of each. And if you're using Vec4s, then you have to specify the A. I'll talk a few minutes about the A a little bit, but generally you're going to want to have the A equal to 1 now, saying that's the surfaces are opaque, and the 1 for the light source can have some weird effects, which we'll see here and there. But generally that'll always be a 1. The ambient diffuse specular, I have the 0 on there to just say that would be source 0 in case you had multiple sources. Light position is the other variable we have to specify. That's an x, y, z. We'll specify it as a point. Now, if we have the 1 there, then that is our homogeneous coordinate representation of a point, and that says, oh, that's a finite location within our space. Now, notice also that we're specifying that in the same coordinate system as our vertices if this is, say, 4 lines of code in my application. Now, what happens if that 1 for the A component is a 0? Well, if all of our mathematics works and we do this carefully, that changes what's called a positional source, meaning that it's located a finite distance from the origin into a infinite or distant source is what it's usually called, where instead of the light from that point source going out in all directions, the light is coming in parallel rays. And so it's a far source or a distant source, and if we've done things carefully, everything will work out fine when you change that 1 to a 0. Okay, now direction, this is what I just said, is that the 1 and the 0 actually can be used there. There's some other advanced effects you can get for using values in the middle. I've again left out the distance term. You can add the distance term if you like. Since you're going to be building up the models yourselves, it's fairly simple to add. What about spotlights and cutoff? These are the functions that used to be in the fixed function pipeline. For a spotlight, you'd specify a direction, a cutoff, which would be essentially that angle. So it would be 0 except between minus theta and theta. And you could also have an attenuation. You could have across the spotlight. So going as again a cosine to a power, because that's easy to compute by just looking at dot products to get the cosine of this angle. So it would be cosine to some power, and that would be more like a real spotlight, that you had the highest intensity at the center and then it would drop off at some rate. So these are very easy things to add to your own code. So I don't think we're losing much by having those functions being deprecated. Ambient, what OpenGL used to have, again another deprecated function, was to have a global ambient term that was not dependent on the lights being turned on in the scene. Now, I should have said that a little earlier. The old fixed function pipeline, what you would do is you would set all these parameters, but you'd also have to enable each light source. So you could turn lights on and off in your program very easily by just disable, enable, disable, enable, so you can have as many or as few as you wanted. So there was also a global term in there, and that wouldn't depend on any of the lights being on. And often people use that, but just for testing. So instead of having the lighting model being applied, which could also slow you down and you had to apply all these parameters, just to see if everything was working correctly, you would use that global ambient term with a small amount of white light. Moving light sources, very straightforward to do because a light source is a geometric object. It's like any other geometric object. So if I change the light position, the direction of the light or its location, if it's not a distant source, or even if it's a distant source, are going to change. Now, but also it should be affected by the model view matrix. But whether it is or not is going to depend on where you place that light direction in your code. So you can have all kinds of combinations depending on where you specify relative to where you specify a model view matrix. So if things are being animated, there's a time variable, say moving things around and you're re-rendering, you can move the light source with the objects. You can attach it to an object. You can fix the objects and move the light source. You can fix the light source, move the objects. You can have both of them moving in different ways, and it's probably a good exercise with some of these simple things we're doing to actually try to get the combinations you want of light sources and objects moving or not moving, but you have a tremendous amount of flexibility, and it's just a question of where you place things relative to setting or changing the model view matrix. The light properties in terms of specifying them are pretty straightforward. You just specify the red, green, and blue components of the light source. I think we just talked about that, and you specify a position. This is probably extra slide I just recopied. So that's it. Oh, these are the values actually we're going to see in a minute, or at the end of this lecture, when I just show you the rotating cube. And here's a more typical situation where the specular and diffuse components are the same. They're just going to be white, and I'm just going to put a little bit of ambient light into that scene. So, but since the components are equal, it's grayish kind of light. So if we're going to see any color, the color is because the materials are going to absorb differently for red, green, and blue. Okay, so let's turn to materials. So here's very simple. You specify them to match what we had in our light model. So for the ambient, diffuse, and specular, there are going to be absorption coefficients for the red, green, and blue components. So there's an ambient term, there's a diffuse term, and there's a specular term. So if you look at these here, what is the ambient term is it's red is fully on and blue is fully on, so it's sort of a purplish ambient light, but because it's getting multiplied by very small numbers, it's probably not going to be very dominant in our scene unless all of the diffuse and the specular light is absorbed. So you're probably not going to see much of that in the example I'm showing. What you'll see primarily are these two components where for its diffuse and specular, the red is reflected totally, the blue is slightly absorbed, and none of the green is going to be there. So you'll see this, so you're going to get red and a fair amount of green, and that's going to be a yellowish, you expect to see a yellowish kind of color. Now we also have to specify the shininess, which is just a constant. So this is a fairly shiny material I'm going to make, so it's going to be closer to being some sort of polished metal when we look at the result. Now, none of this has had anything yet to do with anything in MVJS. So MV.js. So let me give you a few helper functions that we've stuck in there. Okay, one is that if you notice that we're always multiplying the components of the light terms with the corresponding components of the material terms. So we say, well, let's create a function that does that. Actually, we don't even need a function. We can just use the mult function that's already in there. And when the mult function is given two vec3s or vec4s, it will then multiply them component by component. It detects what the size of the entity that you're putting in is. So I can get these ambient product, diffuse product, and specular product, which is just multiplying together the K's and the intensities, and that will really the decay for each diffuse or specular ambient cone with the corresponding one for the material, and that will sort of make the code look a lot cleaner. Now, if we're going to do the calculation in the shader, then I have to get this information to the shader. So what I'm going to do is just send them over as uniform. So here's the standard uniform way of sending them over. They're four-dimensional the way that I've done them. So I'm going to get the uniform location for the program. I can combine this all in one line. Get the uniform location from the program object. We're going to give them the same name in the shader: ambient product, diffuse product, specular product. And then I have to run them through the flatten function, because these things that are here are objects in JavaScript. They're not simply arrays of numbers. So flatten will recognize the size of this and extract the four constants out of this. Likewise, I do that for the diffuse product. I do it for the specular product. Also, same thing. Position is also a four-dimensional variable. It's kind of nice that because so much is four-dimensional, RGB, A, X, Y, Z, W, that we get to reuse the same functions over and over again. It makes the code much simpler. And finally, I use the shininess is just a single float, so I use GL uniform 1F, get the location of something which will also be called shininess in the shader, and send over the material shininess. Okay, so that's how I get the information to the shader, and this is assuming I'm doing the calculation in the shader. I'll talk a little bit more in a while, or in the next lecture, about, well, why don't we just compute vertex colors right here in the application. And in fact, you can do that. You can apply the lighting model. Don't worry about this stuff here, sending it over. Compute some vertex colors, treat them as any other attribute, and send them over just as colors rather than as things that will help you do the lighting calculation in the shader. We'll talk a little bit more about it. It's certainly doable. It's probably the least efficient way to go about it for anything but a really simple problem like I'm going to show you with the cube. Okay, what about the normals? Well, here's a little function that can use the MVJS to help you compute the normals. This is exactly what we had before. The quad function we've been using gives 4 vertices, and it generates 2 triangles from that. You can have it generate a triangle strip for the 2 triangles, a triangle fan, or just 2 separate triangles. That's not crucial here. So I have this quad function. It takes the 4 vertices, which it's assumed are circled in a counterclockwise direction for an outward pointing face. So since the normal is the same over the whole face, if this is a flat quad, then I can just use the first 3 to determine the normal. So I subtract b minus a, and then I subtract to get a vec. Let's see, it doesn't matter whether it's a vec 3 or vec 4. We've taken care of that. It's probably vec 3. Then c minus b will give us another vector, or c minus a if you want. And then take the cross product of the 2. Now I have to normalize that. So I'm going to say, make this a vec. Oh, okay. So I see what's happening here. If these are vec 4s. This is going to give me a vec 4. I can take the cross product of 2 vec 4s. If I give it 2 vec 4s, it will say, hey, ignore that last component, which will turn out to be a 0 here, because you took 2 points, you subtracted them, and they both had 1s for the 4th component, so they stick a 0 there. That's what we want to happen. But then when I take the cross product, the way it's written now, it will give you a vec 4 with that 0 at the end. So this thing will simply say, hey, throw that component away, give me a vec 3. Now normalize that vec 3, and now this can be treated like any other attribute. So if you look at the rest of the code, it looks just like what we had with the quad function before. You push the vertex location onto a stack. You push on the normal at that point. this is one way of doing it, because this would work if the normals were different at every vertex. But we're going to push it on, 6 times, or if we do 2 triangles. But you do just push that onto a normals array, then push vertex B on, push the normal again, push vertex C, and so on to get it. So it'll look. This is in the rotating cube under chapter 6, which I'm about to show you. You may also want to worry at some point about front and back faces. For convex objects, what we've said before is that you're not going to see a back face, and so the examples I'm showing you now, you don't have to worry about it. But if you do something like you slice this sphere or take a side off of the cube, then you're going to be able to see a back face, and now you have to render a front and a back face, and they could have very different material properties. But it's all very, very doable within your own code. Okay, we haven't said anything yet about emission. You can add an emissive term. The way it's done in WebGL is when people were doing scenes of rooms, they would say, "Oh, what if there's a fluorescent light in that room? What do I do with it?" It's well, one way to think of it is you treat it like any other geometric object. You can model the lights in the room with polygons and display them. The problem potentially is, well, what do I do under lighting? And what the old fixed function pipeline did is, what the emissive term would do is it would simply be like any other geometric entity and polygons, but it wouldn't change its color by any lighting calculation. So if you had a big white square up on a big white rectangle, say, up on the ceiling that was supposed to model a fluorescent light, no matter how you change the lighting from other lights, that would always give the same contribution to the scene. It would just be this white polygon in there. It wouldn't do anything else. So it's kind of doesn't look that great, but it's probably the best you're going to be able to do without having some more complex lighting model in a non-pipeline kind of rendering. Now, one other comment I want to make before we look at the code is to say, what about transparency? The fourth value, A, is what makes the surface transparent or translucent. It gives it, if that A is 0, it says the surface is totally transparent. We're gonna talk about that separately when we start talking about compositing in a few weeks. The one thing to keep in mind is leave it at 1 for now. Generally, in OpenGL, you had to enable that facility. If you wanted to have transparency, it was something you had to enable. It was called blending. Things blend together because you can see through them, so you would enable blending or disable blending. The problem is with HTML5 and using the canvas element, things get more complex, because in the old days, if you didn't enable blending, and this was true in desktop OpenGL with or without the deprecated functions, as if you didn't enable blending, it didn't matter what you did with the fourth component. It would always treat it like 1. The problem with HTML is that you can combine other applications on the same canvas. And so what's done with WebGL is if you set A to be 0.5, even if you haven't enabled blending, it will mute all the colors by a half. It will take the RGB you give it and effectively multiply it by 0.5, each of those components. So the reason for that is you may really want to be able to blend things together. So for example, text is not part of WebGL. You may use some other application to get text and annotation onto some graphics that you're generating, and this will help you by being able to blend things together the way you want. But for now, I'd say just you're getting started, we're only worried about the graphics. Just leave A as 1, and you shouldn't have any kind of problems. So let's just look for a second at that application, and that'll sort of get us onto the next way when we really deal with more complex surfaces. So let me look at that application, which is called Shaded Cube. And here it is. It's the same old cube. We can change the direction and rotation. Now notice that flashing coming off. That's the specular term. If you took out the specular term, these faces would be colored exactly the same, because the diffuse term, the normal is the same everywhere. The diffuse term, it doesn't have a directional component towards the viewer, and that wouldn't change at all. So you are seeing the specular term, and this is, remember in this case, the ambient was very small, so we're not really seeing that, and the light for the ambient and the specular were the same, and that you're really seeing that highlight very nicely. But here, it doesn't matter too much where you, at least visually, where you did the computation of the shades, because it's flat across the entire surface. So if I computed the model in the, let me toggle that, if I computed the model in the application and just assigned a vertex color based on the modified Phong model and use that color, the shaders could be just passed through shaders again. If I did exactly the same computation in the vertex shader, it'd be pretty close. But in general, that's not the case. And what we're going to look at more to get a little more are things like this. Here, let me just put this up once, and we'll be talking about that. Here's a sphere. And I'm not going to go over the recursive way of getting that, but here this is composed of a number of little polygons. And now, because remember last lecture when we talked about the sphere having a normal which is different at every point, now how I set the normals and where I set the normals and where I do the shading calculation is going to be very, very different. So in the next couple of lectures, we're going to see the difference between doing the shading in the vertex shader and doing the same, what looks like the same calculation, using the same model, but doing it in the fragment shader. And that's really where you're going to want to be doing the lighting. Another reason for that is that if you do your lighting in the shaders, then you free up the CPU to do other things. And the shaders can do it very, very efficiently. And this is what we're going to be talking about in the next couple of lectures.